How are you guys? I'm going to talk today about restoring Apollo hardware. I'm Marc Verdiell, better known as Curious Marc on the tubes, et Jean-Marc pour les intimes qui parlent français. I'll do the talk in English so it can reach a wider audience. At the end, I'll take questions in either language, in French or English. So anyone has followed the restorations on YouTube? A few? Oh, okay, great. Okay, that makes me feel good. So this will be a bit of an ambitious talk. I had previously given talks about the computer, about the DSKY, about the communication system. I never tried to do all three at the same time. But the reason I want to do that, because I want to show you our latest work where we bring them all together at the end. So I might have to go a little fast, and we'll concentrate on the great moments of the restoration and gawking at beautiful hardware. So this restoration is obviously a team effort. It's way too big for one person, so I've listed the main contributors here in alphabetical order: Carl Clounch, Eric Schlepfer, Ken Sheriff, Mike Stewart, and myself. We had a few sponsors along the way with special thanks to Samtech, my employer, Lumefield startup in San Francisco. You'll see their work in PCBWay. And of course, last but not least, the people that lent us the beautiful hardware: Jimmy Locke, Marcel De Paulus, and Steve Jurvetson. List non-exhaustive, many people have helped us along the way. Okay, so there you go. So this is obviously the command module from Apollo with the protective panels removed, and all the colored boxes is what we have in the lab right now. So we have quite a bit. I'm going to talk today about the Apollo guidance computer, the orange box in the middle. Its attendant display and keyboard unit, the DSKY on the upper right side, also in orange, and all the yellow boxes that form the communication system. And if I can make that work. And we'll start with the AGC and the DSKY. So the Apollo guidance computer is the big golden box here. And for completion here, there are two AGCs in the Apollo rocket. There is one in the command module, and there is one in the LEM. So it's the same hardware, but running different software. But for completion, there is another computer made by IBM on the Saturn V in the instrument unit. That's the one that does the guidance of the Saturn V. And with the backup actually being the Apollo guidance computer. And in the LEM, there's a backup that's called the AGS, the AGS, which is a much smaller machine, just pops you back up into orbit. It's more like a Kim-1 kind of a computer. But the AGC is by very far the smartest of the bunch. And the quote you have here is by Dan Lickley, who was in 2019 at an interview at the Computer History Museum, where I also volunteer. And Dan Lickley is one of the original programmers for the Apollo guidance computer. And the first question he was asked is, what does the AGC do? And then there was a few second pause. He thought for himself, and he answered, it did everything. And it's actually true. So the computer does inertial guidance, navigation, and autopilot. So at its base, and when it was conceived originally, it was a computerized inertial navigation system. So a IMU, an inertial platform, coupled to a computer. The computer does the calculation for the IMU and tells you, which direction you're pointing, in which orbit you are in. I'm going to cough every 5 slides. I have some kind of reaction to the COVID vaccine, so it's fine. It just makes me cough every 5 slides. But it evolved to be more than that. It evolved to be the digital autopilot for the command module and for the LEM. So the entire thing was fly-by-wire, and it's actually the first fly-by-wire digital system. And the computer actually orients and stabilizes the spacecraft. So when in normal mode, there are some backup modes where it's more manual, but in normal mode, when you put an input through the joysticks, the computer reads it and then figures out how it has to fire the thruster, so it behaves basically like an airplane. Like if you go right, it will do and keep holding the stick to the right. It will just do one puff of RCS to do the right rate of rotation and stop there, despite the fact that you are still holding the input to the right. On the LEM, it's even more intense. Because the LEM needs to be balanced on the throttle, right? So it does that whole calculation of doing the throttles, you're at the right descent rate. So even when Armstrong took over manually, as it said, in its landing of Apollo 11, he was still doing it through the computer. So the computer was balancing the LEM the whole way through. So if the computer had quit at that moment, that would have been quite painful. So as we said before, it's just regular navigation, keeps track of your state vector, calculate orbits, knows where you are in the sky and where you are going to go. It performs the burns and calculate the burns, although most of the time it was calculated on Earth and uploaded from Earth if they could do it totally independently from the AGC. And actually, they did calculate at the same time as Earth. So there's a famous line where they are on Apollo 11. They are calculating the descent orbit burn, and the huge computer on Earth does it, and they do it too. And there's one guy say, "Oh, did you see the AGC came up with 0.01 second of ours?" So it could do it totally independently. Guys, LEM to landing. So that's super important function. This is suicide burn, right? You have enough fuel to get to zero fuel, zero velocity and zero altitude at the same time. And that was not considered flyable by a human. It also guides, and this I didn't know before the restoration, it guides re-entry. So the re-entry is active, which is why most of the time the command module would land a few miles from the recovery vessel, which can't be saved from Soyuz, which was just a passive re-entry, and it would land 100 miles from its spot. And finally, it also controls a telescope and optics, so you can align the platform, or realign the platform on stars, which they do at regular intervals before every burn. So a very intelligent machine. In terms of hardware, it's a pioneering system. It's very small at the time where a computer filled a huge room. So 1 cubic foot, 70 pounds, 50 watts. It's the first-ish computer to use ICs. So I say first-ish. The slide used to be first. But it turns out that there might be some other military computers that we don't know of that also switch to ICs at about the same time. So it's the first reported use of ICs to make a computer. The software is really amazing and groundbreaking. So groundbreaking, real-time multitasking OS, and it's checkpointed, which means it can recover if it crashes, which it did several times in the Apollo flight, where you have a 1202. It's actually a crash. It would be a blue screen on Windows. But it's the AGC, so it's checkpointed. It's okay, the hell, I can restart from where I crashed. And it comes back. The first time it did it, I didn't even realize it restarted. It does it in 1 second, something like that. So I'm still waiting for that feature in Windows. And it's designed by the clever and adventurous folks at MIT, built by Raytheon. And I know that shows in how innovative the design is versus the IBM computer, which is very stodgy in comparison. All right, and this is Eldon Hall, is the father of the AGC, principal engineer working at the MIT Instrumentation Lab. So remember him, he'll come back later in the talk. where did our AGC come from? It's a question I get often, and it comes from this LEM, which you can still see today at the Johnson Space Center. This is LTA-8, and LTA-8 did fly, but it flew on Earth in a vacuum chamber. So that's part of, they flew an actual mission with the astronauts in there in vacuum for several days, right? The one in the command module, they stayed the whole 10 or 14 days, whatever. And that was used for man-rating the LEM, that the LEM was survivable. So an important mission that's not, the story is not told often. And after the Apollo program, this computer was decommissioned in 1975, obviously to make room for the shuttle program. And it's government rules, so you cannot just give it to the engineer or your uncle. You have to dispose it through an auction, and nobody wants of the hardware. So most of it ends up at scrappers. And so does our AGC, goes to the scrapper. It's my 5-slide cough. But this man, Jimmy Locke, saved it from the scrapper. So Jimmy had, like many people in Houston, he had worked very shortly, I think a month or two as a NASA technician. And he's also, he likes all hardware that's on the cheap, so he goes, like us, to visit scrappers to get parts. And one day he's at a scrapper, so obviously close to 1975, and he recognizes the Apollo hardware. And of course he can't resist it, so he asks, no, can I buy some? And the scrapper goes, please, I don't want it. It's super hard to recycle. It's full of weird materials. You can have it. And so he buys 2 tons of it, the whole lot, not knowing that inside the pile is the AGC. And he has pretty much spent the rest of his life selling bits and pieces of its pile. Then Mike enters the picture. Mike Stewart is you'll see, very brilliant, and you probably got it if you watch the video. A space engineer, he writes embedded software for satellites, and is a fanatic of the Apollo program, and he's on a mission to reproduce an exact AGC that works exactly the same way, so he can run the original programs on it. And in his work, he realizes he's not going to make an exact replica if he doesn't have access to a real one. And he reaches out to Jimmy, who shows his computer, the equivalent of VCF, but for space nerds, which is SpaceFest. And Jimmy says, sure, come, beep it out. And while they talk, he learns that Jimmy would love if we could repair it someday. And then they say, well, why not? And he reaches out to us because we have been well known for our high profile restorations, particularly the Alto at that time. There's just one problem, is that Jimmy cannot be separated from his AGC. So, and he doesn't want us to, Jimmy is a man of very simple means, and he doesn't want us to go to his place either. So Mike rents a hotel room suite for 2 weeks in Houston, and we get Jimmy and his AGC at the same time in it, and Jimmy is watching us. And on our side, we drop all our toys and fly to Houston. So we're a go to try repairing an AGC in a hotel room in October 2018, with the goal is to have it functional by July 2019, which you all know is the 50th anniversary of the landing of Apollo 11. And that's exactly how I felt when I saw the AGC for the first time opened up. This is Scott Manley, but I had the exact same reaction. He's normal. So the AGC opens up, and it's made out of 2 trays. There's tray A and tray B. Tray A is the one on the right over there, and it has most. So you see it's made with little modules which are removable. These are all the logic modules. We'll take a look in a second. And the ones where you can see the wiring, those are the 2 redundant power supplies. Tray B is all memory. You can actually see the core memory, all 4 kilobytes of it, in the middle, the black module. And then if you look at the way at the bottom, you'll see space for trays. That's where the fixed memory goes, which would say ROM today. And we don't have any. And the rest is support circuitry for the core memory and the core rope memory, which is the fixed memory. It takes quite a bit of electronics to run core memory. So that's reassembled, and then we pop the top cover. So on both sides, we'll have this wonderful wire-wrapped backplane. And wire wrapping was considered, and actually was, more reliable than soldered backplane at the time. This is, by the way, all made by CNC, right? This is not made by a human. There's a machine that's computer controlled that wires that whole thing. More CAD than you think in the 1960s. Ours is Ray 14, so Ray is for Raytheon, of course. And it's number 14 of an engineering series of 15. Those are identical to the flight ones, but they are the torture unit, plus the ones that are used for man qualification for the first vacuum missions. And one of the great things about Ray 14 is that its modules are not potted. So usually this is covered in potting in some kind of very hard plastic, and you can't repair it. But here, most, but not all of the modules are not potted, so you can see the inside. You can see all the ICs in there. There's the same on the other face, so 60 ICs per face, so 120 ICs, and each IC has 2 gates, so 240 gates per module. And that's a close-up. So if you look at it, it's all the same IC everywhere, and it only uses one type of digital IC in the whole computer. And that was made on purpose because they had to spin up the reliability and the manufacturing of ICs, and Eldon says, okay, if I can just choose one part, it will be way easier. That's what he does. They are all 3 input NOR gates, which sit, and I had a hard time believing it, on the 7-layer PCB with blind vias. And as you can see, they're surface-mounted parts, which are welded, once again, stronger than soldering, which is mind-boggling, right? In the mid-1960s, this is technology that would only be available to the general public 30 years later. So all modules are not potted except 2. So we have, that's one of them, that's how it looks, it's all black. And that one is current switch B11, is part of the core memory control. And when we look at the numbers on it, we can tell that it's not part of our original build. It has been put afterwards, so it was been swapped with the original module, which is why it's potted. The other one is the core memory module itself, where the little ferrite cores are. And also, we can tell it has been swapped, not original. Mike is super prepared, knows the AGC inside out. In fact, he has gotten the original schematics from Eldon Hall himself. So he tracked all the engineers down until he found the schematics. And you can see it's all the same gates everywhere, 3 input NOR gate. After he beeped the computer, he was able to achieve his goal, make a perfect replica, gate exact, and we used it many times in the restoration, and we found it to be 100% exact, including the little glitches that you see in the bottom, on the lines towards the bottom. There are some glitches. We saw the glitches in the real one too. It's that exact. So we start by checking each logic module separately, and to our surprise, they all do work. The power supplies check good, no electrolytics in there. There's a few caps, but they are no space-rated tantalums, and they check good. We start them under load, supposed to be 4 volts. It comes up at 4.00 volts. However, it's not all rosy. The erasable memory B12, one has been swapped, checks bad. So core memory is pretty simple. You have a grid of wires going both directions with little ferrites in the middle. So to test it, you take an ohm meter and you test the wires at each end. And one of the wires is open, and it's inhibit line of bit 15. And that line is used on all the bit 15 of the memory. So all of our bit 15 is zapped. Actually, we can't write to it. We can read it once, and then we would lose memory. So that's a bummer. We don't have RAM, basically. And then on the ROM side of things, it's not that much better. We don't have the core rope modules. Instead, we have two unknowns modules, which we think are core rope emulators. So core rope is a little tray like this, and that's where the software is held in permanent memory. And it's a form of woven memory. So you make a bit a 1 by putting the wire in a large core, so you see all the large cores, and it's a 0 if it goes around the core. Very robust, very dense, so they had the whopping 72 kilobyte of ROM, but hard to manufacture, takes 3 months to make a set. So when you do software development, that's not what you want, and we think that's why they put something that emulates what rope would be to the AGC, but the software comes from another computer that is external to it. However, there's no documentation, no mention in anything that we know of, so we have to reverse engineer it, and we volunteer Mr. Ken, and he goes right to work reverse engineering his unknown box. However, so we have a computer with all the logic modules that work, but we have no ROM and we have no RAM. Mike, however, who knows this thing inside out, reasons that if we power it in reset without RAM or ROM and release reset, it should try to fetch the first word in memory at a particular start address in memory, and we should see an entire instruction cycle, which is divided in 15 subcycles, and there's a little impulsion per cycle. So we wire up my logic analyzer to try to catch that, and to our surprise, as the first power-ups, the first trace that we get, and you see at the very bottom, we hold it in reset, then we release it, and we see the 15 subcycles in nice succession, which we didn't expect. Not only that, but there's another cycle afterwards. So it got the garbage instruction and is trying to execute it. So this is super encouraging. We weren't expecting that at all. So we're probably a week and something in after having checked all the modules, and we're super happy. And at this point, brilliant Mike has a brainwave and he says, hey, wait, I have another one of these FPGA modules that I brought with me, the same one I made my AGC on. I think I can whip up a memory emulation FPGA. And he goes on bed and works for the evening, and he does it. The next day, we wire it up into the computer, so we have that horrible Frankenstein setup. The day afterwards, we debug it with the logic analyzer, and eventually, we get it to work, kinda, and Mike loads Apollo 11 software on it. We turn the computer on, it boots, and it starts to execute the Apollo 11 program. Not perfectly, it crashes after a few hundred instructions, goes bananas. But this is almost incredible for us, because for it to do 200 instructions or something like that, a lot of things must work. So we're all super happy, and we're at the end of our 2 weeks, so we have to leave the AGC and Jimmy behind, but we don't come home empty-handed. I get custody of the memory module. We try to X-ray it at Samtec, and the hope is that the wire break is near one of the output pins, which is a failure they had seen in the early modules, in which case we can maybe dig a hole and repair it. Unfortunately, all the wires appear fine on the X-ray, so it's not that simple fault. Then we try more experiment in the lab. This is time domain reflectometry. So we send a pulse in the wire, and if it's broken, it will reflect at the other end. And you can see it happen. I have two traces. The bottom one is a good wire. The top one is the broken wire. And at some point in the middle, they diverge because I'm getting more reflection. And it tells me that the reflection is in the middle of the module. So the wire is broken right in the middle of it. And we do some more experiments in the frequency domain, tells us the same thing. So B12, forget it, we can't repair it. Carl is our prop master, so he makes a DSKY replica. Another problem is that we need to connect the thing. It has two connectors, the main connector on the left, and the right is a test connector, and it uses a pin that's called a Malco pin, that we have only seen in the Apollo program, and it's unobtainium. Fortunately, I do work for a connector company, and I asked them if they could redo the Apollo pins, and they say, sure, we'll try. Give us the drawings. And Mike finds the drawing in the National Archives, and we give it to the engineers, and they tool it up, which is an expensive endeavor. And we get our new old Apollo pins and can make connectors. During that time, Mike is also working on the monitor, the AGC test monitor. So remember that port on the right, that's plugged into this big monster of a machine, and it turns the AGC into a proper blink and light machine. And the monitor is fairly powerful. It gives you access to all the registers. You can trap register value and stop on there. You can make breakpoints. You can see faults. It's a super helpful box. That's Mike's equivalent hardware, but shrunk down to yet another FPGA, which fits into the connectors thanks to the Samtec pins, as the same connector as was used originally, the test connector. And on his computer, he has the same front panel as the original test monitor, and also a virtual DSKY. So we are now well equipped for work with the AGC in my own very posh basement lab that you see in the videos. And Jimmy is still cannot be separated from his AGC nor his wife. So we have to fly all three. But we're so happy, we're fine with that. We're happy to have the computer, we can work properly on it. So now that we know that the computer is mostly working, we concentrate on ROM and RAM. The first thing we want to do is the core rope. And Ken has now reverse engineered them. However, when we put them in, they don't work. And that will be a constant through the restoration. Like the space hardware almost has any faults in it and works relatively well. The ground hardware, which is not space qualified, is made by the same people, right? But it's not to the same standard, and it behaves like normal 50-year-old electronics. Nothing works. Plus, it's undocumented. So we found disconnected wires, we find bad transistors, we repair it all, it still doesn't work, and we eventually find that we must have cut that box in mid-engineering cycle, and it's incomplete. But Ken figures out how to complete the design. We have to add a few components, like the two caps, which fortunately I had in the same color, so the electrons would not be annoyed. And we finally have success. Mike can tell through his test monitor that the AGC is reading the ROM from the core rope emulated by Ken's box. So we've got ROM. Now, RAM is going to be more difficult. We had not tested the memory module of tray B when we were in the hotel, so we start doing that. And very soon, Mike discovered a fault in module B11. And module B11 is spotted. Oh, by the way, that's the current switching. It's core logic. I'll explain that in a minute, but it's weird stuff. It's an analog module or mixed signal module. We try all kind of chemicals. Nothing does anything to the potting. So in the mill it goes. We mill it down to where we start to see wires. You see the little white wires coming through. Then I continue with the dental pick. And then eventually, I remove all the potting and nothing is broken in no small parts because the wires are not soldered. They are also welded and they really held very strong. And I thought I had done something completely sacrilegious, but it turns out that way later I learned that I did it exactly as Mary did at the time. So they had a lady called Mary at Raytheon to which they would give their broken modules, and the components were so rare that they recycled it if they could, they repaired them. And Mary did exactly this. She dug a hole and to repair the module. So I am the new Mary. Now we can have access. We confirmed that 2 diodes are bad, which is also a failure they had seen in early modules, bad diodes. We drill it out, so it's a construction. The analog modules are cordwood construction. You have two wiring back and front and back, and then the components go transverse, so you just drill it out. We go to Anchor Electronics, which is our source of all components in the valley. They have the diodes from 1965. They still sell them for the price of 1965. We do that over lunch, right? So we get our original diodes back, and then we test it in the bench with the new diodes, and it works again. So what the module does, it generates 2 pulses of different direction, 2 current pulses of different direction to put in the core memory module. So you see the purple traces go down, then goes up. And that's done by flipping one of those giant cores that are the same that are used in the core rope memory. So weird piece of core logic. So we're super happy, we dodged a bullet, and then Mike continues to test the module, and dang it, he finds another fault, and this one looks worse, because it looks like there's a short in the module, and we are afraid it could be between, so you see the little circles? Those are the cores, and there's 4 windings on it that make it flip at the right time, and some that pick up the flip and generate the pulses, and it looks to him like if we have a short somewhere. So if it's in the wiring, that's fine. If it's smack in the core, that's going to be very hard. So another pocket we dig, and we confirmed that there's a short, and we confirmed the location of the short. The short is in the freaking core. So at that time, that's probably our lowest moment in the restoration, right? Going from elation to have it repair it and going to a fault in the core. So those are potted components within the potting, and they're very fine wire. There's no way to take it out and without breaking it. So we are demoralized for a second until we discover that, oh, you know, it's a winding that picks a pulse of an alternate polarity for another winding. Maybe we can use that other winding, disconnect one of the windings so there's no short, use the other winding and put a PNP transistor in it instead of an NPN, and that will work. And that's what we do. We devise an Apollo 13 repair. It's a little bit of snipping, blah, 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 cutting, rewiring. And we put an extra transistor. I don't know if you see it poking out in the middle. With a modern PNP, there's no PNP transistors in the whole thing. And sure enough, you see our purple trace goes up, goes down. The one done by our PNP transistor is the second one. You can see it's much sharper. We obviously have a modern transistor that's way better than the one they used. So we dodged the second bullet and we can even, the repair is small enough that we can tuck the transistor in, which is important because we have no space between the modules. So by this time I have 6 pockets, because there's pockets, each side, and it takes about a day to dig a pocket. All right, so now the electronics for controlling the RAM is good. We still have the problem with our module that's not deemed repairable, but we have a way around it. The AGC is a 15-bit machine, but the memory is 16 because they have a parity bit. So we're going to do the obvious and swap the parity bit for the broken bit. So we'll recover our bit, but we'll break parity, and then we'll disable parity checking. which can be done relatively easily. It's less than a 10 wire of rewiring in the backplane, and it's wire wrap backplane, right? So you can do it non-destructively very easily. So we do that. And now we have RAM, we think we have RAM and ROM, and we even have a Wall Street Journal filming. And here's the big moment. There's actually, Scott Manley is there too, so we will hear his voice if the audio works. The audio is unsynced from the video by about a second and a half, so it might not work perfectly. Well, it doesn't work if there's no audio at all. What should I do? Press the thing again. See if that works. Let me try it. Okay, our audio didn't work. Nice on click share. En rouge. Okay. Try again. We got it to work last time, so. And then we repair an AGC, so this we should be able to do. Okay, can you try to run something on it? Oh, it worked for a second. Okay. Was promising. Oh, okay. If it doesn't work, that's okay. I'll dub it. It's red. Let me try the Heimlich maneuver once again. It's on click share. It's fine. Let's run. Go here. Try it again. Should I try again, or should I click on this thing? Nope. I didn't do a thing. Okay, white, red.
See you again. Okay, here we go.
You have a DSKY hooked up? Or?
Well,
It'll show it here.
Commercial DSKY, okay.
Yeah. Okay, what's current?
174.
Hasn't changed.
Okay, here it goes.
2.27. Oh, it's running.
Yeah, we got it display.
On its own memory.
Yeah, on its own memory.
That's great.
So.
Yeah. So I don't know if you caught that, but the DSKY came up to life. Yeah, the whole thing. So it's first try was a charm there. Yeah, and we for us that was the equivalent of landing on the moon, right? Okay, and we make it to the local newspaper. We are celebrities. Fame and fortune will come to us. So Clever Mike also finds a way to interface the AGC to orbiter, which is why, by the way, he wanted an exact replica of the AGC, because he wanted it to be put the model in orbiter, so orbiter could fly it with the original software, which he had done. But now we can instead have the calculation done by the real computer, because it works with the exact same thing. So we can now fly landings, which, by the way, is pretty hard. But we then take the AGC on tour to the East Coast. So it's a week before the anniversary. We just have time to go there and show the computer flying landings with the Apollo 11 software. And remember Mr. Eldon Hall? Well, there he is in Florida. He was 96 at the time, and Mike flew landing right in front of him on his computer. He has left us since then, I think 2 years afterwards. But we are super proud that he got to see his machine again. And that is the computer on tour. And Mike did many a landing. It never crashed, which is hard, by the way. And we even flew it in front of the original designers and programmers that were still alive at MIT. All right. So that is the bittersweet ending of our restoration. Ray 14 sells in 2021 for the eye-watering sum of $750,000 US. that was the deal all along. So no surprise for us. That's no, as I told you, Jimmy is no wealthy person. The AGC was going to be his retirement. The reason he wanted it repaired is to bring up the value of the AGC, which it did. So we were very happy for him. What surprised us is that the buyer paid a healthy premium to get a working computer. So we expected a call back because you cannot power it up if you don't have our tools, our connectors, and all that stuff. We never got the call. So we don't know where it went. So for now, we have been using Mike's replica since then, and we hope that we'll get the call one day. So moving on, how am I doing? Well, okay, a little behind schedule, but not too bad. So to cheer us up, one day, Marcel, which is one of the large collectors that gives us a lot of the stuff, casually comes in the lab and brings a big bag or big box, and inside in the bag there's this thing, which you have guessed because it's written on it. It's written on the slide. It's a DSKY. So he had bought an actual Apollo DSKY display keyboard DSKY, and that's the interface to the computer to the astronauts. For another eye-watering sum. And so that's where the DSKY, one of the DSKYs, there are two actually in the command module, but no, very prominently used at the center of the command module control panel. In the LEM, it's of course just how you're doing the landing. You can't live without it, and so it sits between Neil Armstrong and Buzz Aldrin. And we kind of know where ours comes from. It comes from MIT, an MIT simulator, but there weren't that many simulators in MIT. And ours has the light arrangement for command module, so we think it comes from this, the command module simulator that they had at MIT. That's a period photo. It had a little accident, and it has a huge ding at the back, so it was probably dropped. How does one drop an AGC? I don't know, it's behind me. And what it broke is the electroluminescent display. So LEDs were not invented yet, would be a few more, 5 or 10 years. And they didn't want to use, they tried to use just lights, but it went too hot, consumed too much power. So they went for electroluminescent display, which is great, like kind of a phone screen, is flat, compact, cool to the touch, vibration sensitive. The one big downside is that you need high AC voltage to light it up, 250 volt AC at 800 hertz. And it also not that long-lived. It loses 60% of its brightness pretty quickly. The electronics in there are, it's a relay computer. I saw a fantastic relay computer in the show. That's what this uses. So it's a latching relay which solves two problems. It solves the switching of the AC, which there are no transistors to do at that voltage at the time. It also solves the memory problem because the relay is latching, so you have screen memory which is mechanical. So you have one winding to latch it, one winding to unlatch it. And sure enough, when we open it up to check it out, we see all these green modules inside, and those are IDMs, what is it again? Indicator driver modules, but they are a box of relays, basically. And up, let me see if I can go back. And at the top left, that's the power supply. So power supply and then relays. That's basically what this is. Opens up in two, like the AGC, a similar connector, similar construction. The white stuff is the kind of a soft spotting. And the little module in the middle of the picture is the diode array for the keyboard matrix. And the top cover is magnesium, as is, by the way, the casing of the AGC. It weighs absolutely nothing. And it's very modular. You can just pick up the screen, unscrew it, but it has a connector at the back, lifts up. We have a few bad keys, one very bad one that has been removed here. But the key doesn't have the contact. The contact is that silver kind of parallelogram behind it. It's a hermetic contact. Hermetic switch, you can still buy it. It's still made by Honeywell. It will cost you a few $100s per, so it's a hermetic high reliability switch still made today. And the key itself is super complicated. I didn't film it because it was too intense to take it apart, but it is lit inside, also EL. It has two springs. It has one long travel soft spring and one little spring on the side. That's stiffer, so you can have a good feeling when you have a glove on. And we repaired it, was fine. Now we had one thing that we wanted to see, is it going to relight? And we had made a test setup for the display, so we took our bad display, put it on the test setup, see if something happens. Okay, high voltage.
Yeah, perfect.
Oh! There's some life. Oh, even I have a 1202, even in the right next to the damage. So it did actually relight. And yeah, so that's just normal. That's a blank screen. It'll come back. Don't worry. So this is really sturdy hardware. We were very surprised. Now, of course, it was very dim, and we wanted to replace it. And Marcel had bought a flight spare display, which is why, many years before, which we had tested. We know it's good, and which is why he was so keen on he was willing to pay the price for this disc even with a broken display, because he has another one in his back pocket. It's not exactly the right display. It's from later, at least from the flown mission, where the DSKY is not from the flown mission, but we can adapt it so it fits right in, almost. Mike spins another version of his AGC, which has the interface electronics for DSKY. And we put it all back together with a new screen, and that's the first power up. Lights right up.
Huh? We gotta restart light. That's good. And proceed.
Whee! It's a working DSKY.
Sure is.
1665. You hear the relays clicking?
Things on your keyboard.
That's a good point.
Over here.
Verb 34.
So that just kills the display I put up. I can do a light test.
Ta-da! Everything lights up.
Wow.
Yeah, we're super happy. So we believe that's the only DSKY on planet Earth that works currently. How to read a DSKY, by the way, so you have warning lights or operation lights on the left, you have the keyboard, and you recognize it as some weird keys, verb, noun, enter. This one doesn't have pro, so it's this is a photo of a prototype, pro for proceed. So this is obviously a prototype AGC, DSKY. And then it has three important numbers on the top. The one on the top right is your program number. If you land on the moon, it's 63, P63. When you're doing nothing, you run P00, which is far from doing nothing. It sends all kind of telemetry back to Earth. And then you put a verb and a noun, and this combination of two numbers changes the meaning of the display or gets you in a routine to input something. And you have 3 rows of display. Now, to interpret them is not easy. You have to memorize it because it could be, first, it doesn't tell you the unit, and it doesn't tell you where the decimal point is. That's in your head. And then a number could be an altitude, a speed, a time, a memory address, a value in memory. It could be anything. So you really have to know your verbs and nouns and verbs, your program verbs and nouns, which I don't. So they had them written down actually on the checklist to avoid mistakes. They still did make mistakes. But there is something subtle that's not working, and I'm going to show you the video where we exercise it some more, and you probably know if you have watched the video what's not working. So it looks pretty good, there's something off.
Full screen read.
You have figured out what it is. It's on the upper left of the screen, there's supposed to be a computer activity light that's supposed to be blinking, and it's blank. And obviously you are exercising the computer, so it should blink. And we know it's not the screen because we tested the screen, so it's not that complicated. It must be the relay, right? So we go back in, we take the relay module out, and so we open one up, and you can see all the relays in there, latching relays. Same thing, there's some on the two. No, I don't think there's some on the back on this one. There's wiring on the back. And the computer activity relays on the top right. In the other direction, you can see it's all blue. Something has happened to it, something has leaked. So bad relay. So we could change the relay, but those are hard to find, and we'd rather not do that. And Mike has another brainwave, as he always has brainwaves. And all the IDMs, the relay modules, are the same. And some of the IDMs contains relays that are not used within the DSKY. They are used for something else in the spaceship. In particular, there is one that's used for taking control over the IBM computer, right? So there is one that flops, and if the IBM computer craps out, you can do your own control of the Saturn rocket. And he finds one of those modules which with an extra relay that's unused right at the same spot as our own relay that's broken. So we swap the two. And result here. Now works. You see how it blinks?
You fixed it.
We fixed it.
What do you do?
So we swapped modules D4 and D5. All 6 of the indicator driver modules are identical.
The relay modules
Yeah.
that you just opened.
Yep.
Okay, oh, it loops. So now it works really. So we have the real working DSKY with an activity light. And if your activity light stays green all the time and never goes to black, you are going to get a 1202. When your computer is overloaded. Okay, so now we have an AGC, we have a DSKY. What else can we do? Well, Steve Jervison gives us some of the Apollo communication boxes, and it gives us 2 boxes at first, and then it goes down from there. So I'm going to, you guys still awake? As it's the long part of this video, of this talk here. I'm trying to experiment, see if I can do it. But if you can go through the painful communication system, I'll guarantee I'll put the AGC, I'll have the AGC talk over the communication system, which I haven't shown in video yet. It's quite impressive. So I won't be able to explain it in the time I have, and except it's super complicated. It's called the USB communication system, and USB stands for Unified S-Band. It's unified because it regroups a whole bunch of radio links that are accumulated during the Mercury and the Gemini programs. And it's S-band because they bumped it up to the microwave at 2.1 gigahertz so they could reach up to the moon, which the previous system were in the UHF, they couldn't do that. Quickly see how much I can say. It's a bunch of microwave links. There is the PM uplink that comes from Earth at the sweet frequency of 2.10640625, derived from an atomic clock. So very precise reference goes up. The spacecraft receives it at a different frequency because it's flying, right? And the Earth is moving, so it has Doppler to it. So what it does, it receives it, it translates it by a factor of 240 over 221, and spits back out that translated frequency back to Earth, which turns out to be close to 2.2875. But by examining exactly what frequency it is, you will know the speed of a spacecraft. And both of those PM stands for phase modulation. Both of those microwave carriers have subcarriers in them that carry ranging voice and data information, sort of symmetric. Full duplex, they could talk over each other if they wanted to. There is a backup link, which is called the FM downlink, because it uses frequency modulation. In normal time, it's used for television, recorded voice and data, which you can send, by the way, at the same time the other links are active. So when they go at the back of the moon, they record everything and they dump it at high speed when they're back in front of the moon, and also the scientific data. It's very complicated. Here's the spectra of, what is it, uplink, downlink, FM in 2 different configurations, so it's full of subcarriers modulation. I won't go into it, but it will reflect in the complexity of the hardware. So that's the first box we got, the USB transponder. It has the microwave radios in it. So transponder because it receives and then spits out the same frequency, translated frequency derived from the received frequency. And that's the interior of it. It's just beautiful. Surprisingly, it has no tubes in it. I expected to see tubes at 2.1 gigahertz in 1965. No. It's all solid state transistors. And you can see it's duplicated. So there are 2 PM transponders in it, PM1, PM2. The FM, there's only 1. And then the 2 gray modules in the front, the silver modules in the front are for the steerable antenna, because it moves, it automatically aligns to the transmission. Out of the USB transmitter, it comes about a few hundred milliwatts, so you have to pump it up with a power amplifier. That brings it up to 11.4 watts at the antenna, twice, because we have 1 PM and 1 FM. Which, come to think of it, is not much power coming off from the moon. And that one actually uses a traveling wave tube, a TWT. So that's the only tube we have found. It's gorgeous inside, but it's perfectly fine to use tubes because TWT is what the James Webb Telescope uses today as its power amplifier. So it shows the right technology that's still used today. Very prominent on here is the coax cabling, and that has to do with redundancy. It goes through a bunch of relays that allow you to reconfigure the 2 tubes for the 2 amplifier here. So if the PM fails, you can put the FM at its place. You can also bypass the whole thing, which they did on Apollo 13. So a lot of the stuff, the system is extremely redundant. So in order to test it, we need a ground station. This is honeysuckle. So they had a 26 diameter antenna. Why so big? Because they have only 10 watts coming back down, so they need a large antenna. However, in the other direction, they blast it. They put 20 kilowatts up, so that the command module doesn't have to have a giant antenna to receive it. And we need to replicate this, which is the receiving and transmitting equipment. And we scratch our heads for a little while until we get this. It turns out that in his garage, Steve Jervison had this, which he had no idea what it was. And we inspected it and said, wait, that's a mini ground station. It turns out that's the NASA test equipment that was used to test the system on the ground. So yay, we have a original mini ground station. Problem with it is similar to what we had experienced before. None of the ground stuff works. It's all, it has broken down, but it's worse than that. Some parts have been broken by mishandling, or it's missing stuff. Some stuff has been pilfered, and there is no documentation for it. So the toughest part of the restoration was to get those boxes going, but eventually we do. And that's the transponder mount. That's the one that allows you to test the transponder and power it up. And this is the first time we power up the transponder.
That is the result of your hard work. So now we turn our attention to the 3-phase power supply. We have 3 phases, 115 volts, 400 hertz. Okay, well, that's the moment, right? It probably hasn't worked since 1970 something. Yes. PM1. And a 1 and a 2. And a 3. Yep! It's transmitted. 2.2875. No, all the power we need. smack at 2.2875, right in the middle of scope.
So same story. So remember 2.2875 is approximately the frequency that returns when it's not locked. And no, similar experience to what we have before. The stuff works after 50 years, where all other normal electronics is long dead, right? It's just extraordinary hardware.
That is your...
Okay. That said, we have only revived the yellow stuff, and we need to do all the rest that does all the modulation. So we haven't done much, and that's already where a year in or something. So next up is the PMP by Collins, the small and mighty box. And it's similarly gorgeous. PMP stands for pre-modulation processing. That's the box that does all the subcarriers. You remember the colorful chart? That's the box. And inside is just point-to-point wiring, no PCB transistors. It's welded, once again, no soldering. And it's super complicated. So it has, you can read it yourself, control lines of the wazoo, oscillators, modulators, demodulators, gates, filters, blah, 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 to do all the modes. So it's super hard to test. We had actually to take it apart entirely to figure out what was doing what, because of course we don't have documentation on the pinout. But it turns out it seems to work. In order for it to work really, it needs its reference frequencies from the CT, which is the central timing equipment, which also doubles as the clock of the ship. And this one is all welded, so we can't open it up. It better works. But we wanted to have a peak inside. That's where startup Luma Field in San Francisco offered to do an X-ray tomography of it. And to my surprise, I thought that only the AGC had ICs in the whole command module. Not true. This box has ICs also. And those are frequency dividers. So pretty good clock, and it also it has the get time, the mission ground elapsed time. So it's 1 day, 20 hours, 3 minutes and 1 second in the spacecraft. And same thing, we powered it up and it worked. We need a control panel, so that's the handiwork of Eric, also known as Tube Time. So what we're doing is a replica of the lower right corner of the command panel that has all the comms controls. Ooh, here it is. And here is the space side of the setup, about 3 years in. So you can see the power amplifier, the transponder, our command panel, the PMP behind it, the CD behind it, and then the two other boxes. Those are the digital links that I'll come to in a minute. And then we have trouble receiving the thing. So that's our main receiver, the PM receiver. And after we checked it all out, 3 repairs, he can't still receive anything. And we soon discovered that the equipment has been modified because it has been used for other missions after Apollo. So they changed all the frequencies, they made all kind of modifications. Fortunately, we have great notes from Mr. Frank Landsberg, and he was a Motorola engineer. I emailed his family, they never responded, so he passed away in 2010 something. But he left great notes that were enough for us to take the thing apart, figure out what had been changed, and it's just full of RF magic. So if you wonder, this is the multiplier for the VCO down there. And the crystal had been changed, so we use nothing but the best Canadian-made crystals. There is a great company in Canada that makes the crystal, and they help tremendously identify what crystal it was that we had to do. So we have a new old Apollo Canadian-made crystal. But you're not done when you change the crystal. You have to retune the whole thing, and it's maybe 20, 30 adjustments per box. Quite challenging. But we eventually manage, and we repair all of our boxes. And here is the first time we get voice going. So you'll see voice is a complicated thing, and you will hear it in the audio of the Apollo flight. Say we we have acquired you. And we are going to do an acquisition, which means locking on the spaceship locks on the up, and the Earth locks on the way down. So we're going to do this double lock procedure and get voice working.
We're getting fairly complete here. So that our transmit station. Here we have the two receives, the PM and the FM. So now we're going to try the grand transmission experiment. Make sure we have. Yeah, got it. All right. So we are transmitting. And I think I'm just going to try to lock it. And now we should have some frequency. We do 2.140. Oh yeah. So then I need to lock it. Locked. And I go to 2.1064.
So that's the return from the transponder is now following Earth. I drag it back.
No, okay. Locked. Alright. Okay, we're double locked. Now we should be able, I think, to get voice up. Alright. Well, let's simplify this. Let's go just do this. Hello. Hello. Do you hear me over there?
Yeah.
Oh, it works?
Yeah.
I'm transmitting voice. Apollo 11, this is Houston. Oh wow, it works!
Yeah, right there.
Wow. Okay, that was easy.
I was expecting some switch settings to be wrong.
Apollo 11, this is Houston. This is my yet to be tested Queen tone generator. Apollo, this is Houston.
All right, we have voice. But voice is, you have seen how hard it is to get going, right? Because of this locking mechanism back and forth. It's amazing that they did it so reliably during the mission. Now, let's try the FM link and see if we can get TV from the moon, which is actually way simpler because the FM, there's no locking involved. It's like receiving an FM transmission from the moon. So here we go. First TV trials.
There we go.
And we've got a signal level over here.
And okay, we receive it.
And we've got a signal on this oscilloscope.
Then here we have to turn it to TV. Is the camera on?
Not yet. Right?
Yeah. Oh, I have it. No, we were transmitting video from the moon. We are. Okay, how many volts do we have? Yeah, a few volts. Oh. Well, that was easy. TV from the moon. Can you move a little bit in front of the somebody? Yes.
Oh,
You have to get a little lower. There.
There he is.
Wow. Say something that somebody can remember. A small step for curious Marc, but.
So we were surprised how good the quality was, but of course we are very, very close, right, from one end of the bench to the other. But we have voice and TV. So next up is what we're working on right now, which is data. No. Keep going. There you go. So next up is data, and this is data down. This is the current videos. I'm over a year back in what I show on video. So that's an important box. That's a box that did the entire telemetry. So all the numbers that you see on here come through that box. And it had both a healthy amount of telemetry points from sensors, hundreds of them, but also the computer would send its whole telemetry and all the navigation stuff, right? So it's made of really weird, I call it alien technology, all those spotted modules, by Radiation Inc., better known as Harris Semiconductor, better known as L3 Harris today, Melbourne, Florida. And is that another video? Yeah, that's the first time we get data down PCM telemetry bits over the air. Right, it looks like we're receiving our first PCM bits.
PCM.
Yeah, Pulse working with like data.
PCM.
And here we see it coming through. I have my bits in green. And then you have now the AGC telemetry.
I do,
Don't
yeah.
you? You probably want to put it back to high bitrate because you don't get very much. Oh yeah, there's stuff going on.
Yeah, right there.
AGC is talking to you. So now you have to decode it, of course, because you get the encoded data stream.
MSK 672, which is the CMC monitor 1 screen. You have the DSKY display right in the middle. So I'm going to start program 61. Program 61 is going to start us.
So we are going to try to read the DSKY remotely.
P61 there.
There you go. And I heard the DSKY say something. Yeah, it came through. So we're reading remotely from the DSKY over here.
Yeah.
So you could read the state of the DSKY display was telemetered back down by the AGC. So you have your own little DSKY in mission control that you can check what the astronauts are entering, and they catch them entering the wrong thing all the time. So when they say, it was plus 23, not minus 23, it's a guy looking at that very screen. That's telemetered down. Right, it looks like, what is that one? Yes, that's correct. Okay, then in the other way, the data comes up courtesy of a Motorola box, and this one is a test box. Of course, on the real missions, comes from a computer, but they have a little test box, which is a repurposed JPL box that they use for actual satellites. It has those those gorgeous displays, and it reads the commands from tape. So they had tape backup also at the station if they had to. The computer couldn't do it. And it's also made from more alien technology from Motorola this time. But it's not really alien. Those are logic modules made out of normal components. That's an X-ray of it, and you can recognize a flip-flop with 2 transistors. So it's just little logic gates made out of regular components and potted in little squares. That's the spaceship side of it. It's called the UDL, Up Data Link. And it's made with the same alien technology, but the space-qualified version of it, so they're not the same modules. All right, so that's the first time we use it, and we are going to send a very simple command via the Up Data Link, which is the abort. And I would think that the abort would have just descended from the ground, and the whole ship separates in pieces, and it aborts. Nope. It lights up a light in front of the astronauts, and it's a confirmation. It's a second confirmation from the abort that they had gotten. I have had a radio, and the astronauts have to react to it. So all the abort signal does is light up a little light in the command module. My old test tape of data. Try to see if that works. Okay, 000 at the start. So that should be abort 1. I'm going to tape stop it and give you the command and see if it clicks. That's it. It did. Light up abort. Then I keep going. And I can extinguish it too. Going to be clear abort 1. Sending it. Ta-da! All right, we have command of a spacecraft. So the significance of this is that we can now control our AGC. So the way you control the AGC via the updata link is you send key presses. So there's a code for each key, and you just type in the DSKY, and that's how you do all the work on the computer. And so now we're going to put it all together, the communication system, the AGC, and the DSKY. We are going to send, from Houston, we're going to play Houston Control Center. And we're going to send a nav update. So the navigation computers with initial platform knows its position and its speed, but if you have a better fix from the Earth data, you upload it, right? So it's X, Y, Z, X dot, Y dot, Z dot, and a time. And so that's done through a verb 71 update. And we're going to do that from the Guido console. So we're now in Houston, one of those console that you have all seen in the movies. And the sweet part that we're going to use is the one on the right. That's circle here. And this is our workspace. So we have a screen for data on top, and then we have a load number panel, which is 23 and 17, where you can punch it and retrieve the data that we want to send up. You see on the right, there is a panel that has also verb, noun, and enter at the far right. That's a DSKY thing. We can type on the DSKY if we want to. And the one underneath is the status of the uplink, because it's not uplink from where we are. It's uplink from, let's say, there's 3 stations that can uplink. There's Goldstone, California, Madrid in Spain, and Honeysuckle in Australia. So let's say it's Madrid. So this was the status from Madrid that we read. So the first thing we're going to do is retrieve our load. Now, we just enter the number and our keypad, and we get to the right screen, and it should appear here. And we check that that's the correct load. So that load has been pre-calculated by people with the big IBM, the RTCC, which we had talked to over the phone. And there's a whole bunch of other consoles that you have never seen. There's way more consoles out of the mocker than they are in the mocker that have gotten this. And not only they have calculated it, but they have also uploaded it in the computer in Madrid. So that data is already in Madrid, ready to be sent. Also, another huge console has connected us to the site, and also will be preloaded to connect us to the next site if we miss it, right? So I have now everything I push on the keyboard will go through Madrid. Now I switch to the screen that we were just looking at, the AGC screen, which has the DSKY lights, and it has a whole bunch of words which are blank right now, which are the AGC upload buffer. So the data doesn't go straight in the AGC active memory, it goes into an area that's just a buffer, so we can check it, and it's still emitted back. So this is the data coming from the AGC. Now, to start the procedure, I do a verb initiate, and it knows from the load that this should be a verb 71 upload. So it does verb 71 on its own, it stops. I check that I see it on the DSKY, and I press enter myself. So it's a combination of automated step and manual steps. Then I should see the computer, the DSKY changing to its receive state, and I do load initiate, the second button, and that's going to get the whole upload going, which is going to appear on my screen with the back telemetry. So I see what they have actually received. I check it either by hand or with the compare button. And when it's good, I have to enter by hand verb 33 enter, which is complete the sequence and commit it to memory. And of course, when you do burn data in even a state vector update, you want to check that by hand. So it was all in the end done by hand. So we don't have a console, but we can do the same through our little tape box, and that's the last video. That's my last slide. That's the grand hurrah here. We're going to use the entire system to upload our data to the AGC and see it come back. Do you have the UDL working over there?
UDL is on.
Okay. This is going to be a reset.
Yeah.
Verb. And then to be 70.
Yeah, and we have a 7 in mainframe.
The 71 made it to the spacecraft. It's over there, and you see it over here too.
Yeah, on our DSKY display on the ground. It's
okay.
also rating 71.
So at this point, I'm the flight controller. I have this screen in front of me, and I'm going to press enter manually from the console. It's going to be sent from Madrid, but the order to send it is going to come directly from a person in Houston.
Right.
So the enter came through.
Okay, so we're in program 27 now, which is the update program.
Okay. And the next one should be 21 enter, which is the number of words we're going to send. 2, 1. So now that's part of the load, and I'm going to do a couple steps slowly, and then we're going to go right through it.
Next one is just 1. That's going to be 1. Enter. Make it.
There it is. Yep.
Made it.
So it's super slow from the tape reader, but in reality, when you can do it from the computer, it would be quite fast, few seconds. And you can see all the data being confirmed by the telemetry down sent by the AGC.
Enter. Okay, and at this point, the automated sequence stops, and I'm the flight controller, and I look at this, and I make sure that all the numbers are correct in the memory.
All of this should be exactly what we expect it to be.
Once this is correct, I have to enter verb 33 by hand from Houston.
Yep.
Verb 3. Enter your work.
Yep, we're back into 2.
And check your orbit.
Check our orbit now.
I've changed.
2. And we're no longer suborbital.
Woo! That's really how it works. It's really the interaction of the updating and the PCM telemetry, which is quite complicated.
Whew. Okay, guys, you're now qualified Houston controllers. Well, that was an ambitious talk. Thanks for giving me an hour and a half. And if you're still with me, I'm open for questions in English, French, any other language I can understand. Over there, you need to get a microphone, I think, to ask your question. Do you have the mic, or you just talk really, talk and I repeat it? Do we have a microphone? Just ask the question.
Have been possible. Sorry, excellent presentation. Congratulations.
Thank you.
Wonderful. Would this have been possible without the use of the latest technologies like FPGAs and other stuff you've used, oscilloscopes and all? Would that have been possible in the past to reconstruct this?
So could we make a replica without using FPGA?
For latest technology that's available for the last 10 years.
With just discrete components? Yes, it is, but it's difficult, right? Because you have to use so many of them and redo the backplane. So there is some activity in there to try to redo it with actual transistors. The difficulty is to get in RTL 3-input NOR gate to get a circuit like that. That's small and integrated, but we're thinking about it. Oh, a question back there.
That was really interesting. Thank you very much. How much of the radio system would you say was made by Motorola? Like percentage-wise, from I've seen everything.
Okay, so it's I wouldn't know how to do the percentage. The prime contractor was Collins. And some of the stuff was, I think the radio stuff was mostly done by Motorola. All of our test system on the ground was Motorola. The digital system was radiation. So it's really a whole bunch of people.
That's what
I would say
in
maybe half, something like that.
Yeah, that's what I've seen in your presentation, and I was wondering because I've been to Motorola headquarters. I work for them, and I've seen posters where they say we put man on the moon, and I was wondering how much of it was really ours.
Actually, they have stuff all over the rocket. I have one of the picture where it says Motorola in the Saturn V rocket, which I can probably pull up after we're done. Can we possibly change the lights and return to normal lights because I can't see the audience. There was another question over here. You have the microphone already? Go ahead.
Oui. En
français.
Oui. J'avais une question à propos des... lorsque vous faites des tests... Can you lower the mic
That's okay. I think it's my mic.
and open up maybe the light of the audience so Marc can see us? All right. Dans le fond, quand vous faites des tests dans le sous-sol, vous utilisez des fréquences qui sont normalement, j'imagine, réglementées. Est-ce que vous avez dû prendre certaines précautions pour vous assurer que l'équivalent, j'ai oublié l'organisme américain? Oui, c'est la FCC, ils viennent cogner à votre porte pour vous demander qu'est-ce que vous êtes en train de faire.
Oui, puis en plus, les fréquences de Apollo sont réutilisées aujourd'hui par the International Space Station.
Oh!
Quand on était en marche, je dis s'il y a le Space Station qui tombe dans mon jardin, là, c'est pas bon. Et donc, ce qu'on fait, c'est qu'on a des atténuateurs partout. Comme on a une très courte distance en plus, donc on n'utilise pas l'amplificateur et on a des atténuateurs en ligne comme on est en dessous de quelques milliwatts. Mais en fait, les pros, ils font pas ça. Quand ils testent leur système S-band, ils font ça dans le labo à plein pot. Mais non, donc il n'y a pas de problème avec notre.
Puis
notre
une question de suivi, est-ce que vous avez essayé ou pas d'essayer de capter les transmissions de la station spatiale avec ce que vous aviez?
Non, on n'a pas essayé, mais ce serait une bonne idée, en fait. Ils réutilisent les mêmes fréquences, mais je suppose que toute la modulation est totalement différente.
La télémétrie doit être complètement différente, mais ça pourrait être drôle de voir si... Avant qu'il l'enlève, parce que dans quelques années, elle ne sera plus là.
Une idée pour les projets vidéo. C'est dur, parce qu'il faut faire du tracking.
Oui.
C'est pas si facile que ça. Donc, quand les gens font ça en amateur, ils font le VHF normalement.
OK. Merci.
On n'a pas encore essayé. Question tout en bas, là.
C'est un projet de combien d'années, ça?
On en est à 6 ans. 6 ans. Ouais, on a commencé en fin 2018.
La construction du premier module, là, ça a pris combien à peu près? C'est le module que tu dois tout monter.
Alors, je ne sais pas à laquelle vous référez. Le FPGA, that took several years, I think 3 years. That started, ça a commencé avant nous, hein, le FPGA. C'est Mike qui a fait ça. Je pense qu'en tout, il a mis 5 ans pour avoir tous les schémas. Mais il a dû aller partout aux États-Unis, retrouver les ingénieurs. Il a retrouvé Don Niles, qui a dit ouais, moi j'ai pas les schémas, mais Eldon, il les a, il est en Floride, il est allé chez lui, il les a retrouvés. Il y a un travail important de documentation derrière. Oui.
Tu as parlé de la puissance d'émission du CM module. C'était 6 watts, je pense que tu as dit.
C'est 11 watts. 11.4.
C'était envoyé dans une antenne directionnelle?
Alors, ils avaient 5 antennes. Ils ont 4 antennes non directionnelles qui sont autour du module. Et ils ont une antenne directionnelle qui est cette... j'ai des photos aussi pour vous montrer. C'est cette antenne qui sort sur le côté. Elle a 4 panneaux et qui est beaucoup plus puissante. Pour faire la télémétrie à haute vitesse, il faut l'antenne directionnelle. Et quand ils sont perdus, qu'ils ont des problèmes, ils se remettent sur l'antenne non directionnelle jusqu'à ce qu'ils aient rectifié la situation.
OK. Puis, il y avait un répéteur aussi sur le command module pour les transmissions du LEM au sol. Ah
oui, alors, j'ai fait qu'une partie du système. Il y a tout un système VHF, il y a 1 million de configurations. On peut parler, donc le LEM et le CM peuvent se parler par VHF et retransmettre sur USB. Donc, s'ils perdent le LEM, et ils le font d'ailleurs dans Apollo, je ne sais plus trop combien, ils parlent au CM et ça revient sur le LEM. Des direct relay, indirect relay, il y a 1 million de configurations. Donc, il y a deux radios VHF en plus. Avec des configurations très compliquées. Ils se mélangent tout le temps, d'ailleurs. Alors, j'ai plein de questions partout, là. Oui. Il y en avait une là en bas, je crois, en premier, ici, là.
Ici, peut-être avant? Là. Jean-Marc.
OK. Oui.
Au niveau du DSKY, celui avec lequel vous avez travaillé, il y avait quelques boutons en moins que les versions prototypes. Est-ce qu'il y avait différents...
Oui, le DSKY a évolué pas mal. Hein. Les lumières en particulier changent beaucoup entre les premiers modèles. Et le clavier, pas beaucoup. Il y a juste Pro qui change. Il faudrait que Mike réponde ça, parce qu'il connaît toutes les versions. On lui donne un DSKY. Ah oui, celui-là, c'est un CM de la version numéro 2,5 fait en 1965. Moi, je sais pas faire ça.
Puis, l'ordinateur qui était vraiment sur la fusée, l'ordinateur d'IBM, est-ce que c'est parmi dans vos plans de retrouver des pièces pour le faire fonctionner?
Alors, c'est plus dur. Parce qu'il n'a pas été publié. Non seulement il n'est pas publié, mais c'était un ordinateur de missiles balistiques. Donc, ils ne veulent pas publier.
Je comprends.
On n'en parle pas trop.
Okay. Merci.
Alors, il y avait des questions partout aussi. Vous pouvez m'aider un peu les gens avec
bonjour.
Vous appelez les gens qui ont les microphones parce que c'est ça qui fait la question. Il y en a une là, il y en a une là. Il y a deux questions. OK, c'est
question bien vite. Est-ce qu'il y aurait de chance de reconstruire une deuxième AGC ou c'est vraiment le seul qui a pu être reconstruit?
Non, il y en a plein d'autres. Hein. Il y a une quinzaine d'AGC qui sont chez les collectionneurs. Donc il y aura une chance qu'on puisse en faire un autre. Il y a les deux cousins des nôtres. Il y a 13 et 15 qui sont ils sont au CMOA, Computer Museum of America, chez Lonnie Mims, qui est très sympa, donc on pourrait sans doute avoir accès à celui-là. 13, il est au MIT. Il y a une moitié, il y a un trait qui est au MIT Museum, qui est aussi très sympa. On a copié les ropes memory. On a pu l'ouvrir. Et puis il y a une autre moitié qui est à Draper's Lab. Il y a celui-là aussi. Il y a celui de Steve Jurvetson, il a le F8. Digital Fly-by-Wire auquel on pourrait avoir accès. Donc il y a plusieurs possibilités pour en faire un autre. Oui, alors, c'est celui qui a le microphone qui gagne. Hein.
Bonjour.
Bonjour.
Je l'ai posé en anglais pour des raisons évidentes. You mentioned that the components are welded and not soldered. Do you have any idea how they managed to weld the little tiny fragile? Did they use a blowtorch or
no,
spot
welder?
Okay.
There's actually an excellent video from MIT where they actually show the process of the people with their spot welder and their microscope doing the spots. It's nickel wire, so it goes fairly fast actually.
Je l'ai dit en anglais parce qu'en français, c'est le même mot, soudé et soudé. Merci.
Alors, déjà quelqu'un qui a le microphone là-bas, il gagne.
You mentioned that you had some media attention for the work you did. Did you have any agencies or investigations from any other CSIS or anything from the U.S. for any of the work? Were they interested in what you were doing?
Oh, I mean, agencies and friendly or unfriendly? With these days, we don't know anymore. Surprisingly, we had no interest from NASA, which surprised us a bit. The only interaction I had with NASA is the lady that did this incredible restoration of the Mocker of the Houston Control Center. And we talked together, and she told me how horrendously difficult it was to have NASA do anything about their wonderful stuff and preserve it. They had all the money had to come from outside. We tried to get access to some items, and we had recommendation from the former Apollo director, and that didn't go through. So there's not much interest from NASA in that stuff at all, for some weird reason. We had great interest from MIT, though. The MIT Museum was so nice to us. Also, we proposed to do landings for the anniversary to the Smithsonian, and it turned us down, but not only that, very rudely, I would say. They could have said just no, but they went further than that. So not much interest from the, I guess NASA, they look to the future, right? They have enough of their past. That's what the people are paid for.
I was wondering, how scared throughout the process you would have been of releasing the magic smoke out of this unobtainium hardware?
So very, very, very scared. So which is why you don't see it, but it's why it takes 6 years, because to power up a box, it's 3 months. Right, we go very slowly, we check that we have all the connections, that we are sure it's not, it's going to a transformer that we expect, that we have several documents that tell us, yes, those are the power pins. If we can do the power supply outside of the thing before, we do that. So it's extremely cautious and a very long process. I try to make it short in the videos, but it takes forever with minuscule
Were there
steps.
any accidents?
No. But it's a valid question. There is a risk, which is why a museum doesn't want to allow you to do their stuff, because they are afraid that something bad happens, which can happen. It's part of the business. When we restore things, we had accidents of other stuff at the CHM, for example, where it goes poof. And it's part of the business, and there's a risk carried with that. But it's very rare, but it's not zero. Well, I have old equipment, so it burns out all the time. It's all electronic, so something will go bad from time to time. I was going to say something else. I forgot what it is. Next question.
Hi. Do you know anything about the Apollo atomic clock system that set the radio frequencies?
It's an HP clock.
Oh, really?
So they had an HP clock at every station, so they could they were sure they were on the. So very important to send the right frequency, because from that frequency and the shift that you get by the double Doppler back and forth, that's how you can figure out the speed of the spacecraft. So it has to be fairly exact.
Cesium clocks, like what you have?
Yeah, same one.
Same one.
Oh yeah, I was going to say, even for when we had our bad memory module, we knew that the Computer History Museum had another memory module in their collection, and we wanted to test if that module had actually continuity in its wire. And even for that, and even with a museum where we worked at, that we know the curators personally, they have seen us work, to get them to have the courage to give us the module and put an ohm meter across the wires, that was a 1-year affair. So that's the amount of difficulty there is to get anything working in the museum, because of the small, but it's not zero risk of doing something bad with it.
Question ici.
Oh oui, pardon, allez-y.
Juste pour savoir, après avoir réussi un défi aussi complexe et titanesque et exotique, c'est quoi vos plans pour vos hobbies pour les prochaines années, là, vos prochains défis?
Répétez la question là, avec l'accent canadien, là, il faut que je m'accroche.
C'est juste pour savoir, après avoir réussi un défi aussi complexe et titanesque comme ça, et exotique, quels sont vos plans de hobby pour les prochaines années? Quels sont vos...
Ah ben, on manque pas de projets. Hein. On peut continuer à Apollo jusqu'à la fin de notre vie, c'est tellement compliqué. C'est une des raisons pour lesquelles j'ai réduit mon travail à Samtech, parce que on a regardé tout ce qu'on a dans la queue, dans la liste à réparer, puis ça ça convergeait pas, quoi. Il fallait qu'il y passait plus de temps. Donc on a ça, on a le Computer History Museum qui maintenant est intéressé à réparer des grosses machines. J'ai aidé à l'achat d'un IBM 650, donc un énorme ordinateur à tube, 14 kW pour le faire fonctionner. C'est pas le beau hardware aux États-Unis, on a beaucoup. Donc le plan, c'est on continue. Si je meurs avec un tournevis dans la main, je serais content.
Merci.
J'ai le micro, donc j'ai gagné. Oh.
Attends, il faut un micro ou
je vais poser ma question, puis après, je vais la donner au monsieur.
C'était une blague, mais on veut entendre la blague. Ah oui, on a du matériel, on a un peu de matériel russe par Steve Jurison. J'ai fait l'horloge, on a fait les horloges Soyuz. Ouais, et on a accès aussi à un control panel de Soyuz. On a trop de travail pour l'instant, c'est notre problème, quoi.
C'était ma question, s'il y avait du matériel russe dans le backlog, donc oui.
Oui, il y a du matériel russe dans le backlog, oui.
C'est bon.
Question par là. Question là.
Étant donné qu'on parle de matériel russe, est-ce que c'est moi qui me trompe ou il y avait beaucoup de choses quand même encore analogiques chez les Russes qui étaient moins présents peut-être chez les Américains?
Oui, non, les Russes, ils ont pris un retard considérable en électronique, et nous, on a pris une avance considérable en électronique à cause du programme Apollo. Hein. On a vécu pendant plus de 50 ans de ce truc-là. On en vit encore, d'ailleurs. Et puisque ça a fait Silicon Valley, ça a fait les circuits intégrés. Et donc, les Russes étaient très handicapés par leur contrôle. Hein. C'est une des raisons pour laquelle leur fusée n'a pas bien marché, parce qu'ils avaient des contrôles très rudimentaires. Ils faisaient tout par la Terre. Il n'y avait pas d'autonomie dans l'espace. Hein. Donc, oui, ils ont pris un faux pas. En fait, qui est bête, parce qu'ils avaient de très bons scientifiques d'avance en ordinateur. Puis il y a eu un édit du Parti communiste qu'ils feraient des copies des trucs de Western Hemisphere, de Western World, et puis ils ont tout perdu sur cette décision-là, ce qui est un peu dommage.
Just wondering, is there any piece of equipment that you dream of working on, or that you would ever like to see or acquire?
Pour avoir des trucs en plus from the Apollo program.
From the Apollo program or otherwise.
Oh yeah, we want the booster, right? The F1 engine. Yes, the one I am missing the most is the DSC, which is the tape recorder, which is it's the flight test recorder. It's an incredible piece of hardware. They had a lot of trouble doing. It can record at 52 kilobits per second, so it can record the full data stream live. And that's the one piece we are missing in our in our setup.
Okay, thank you.
If you have one, just let us know.
Oui. Quand vous avez commencé le projet de l'AGC, à quel moment vous avez senti que vous pourriez réellement en faire fonctionner au complet? Puis, à temps pour le 50e?
À temps pour le 50e, c'est quelques jours avant. On travaillait la nuit, le jour. Hein. Donc ça s'est fait. Je pense qu'on a fini la restauration le jour avant qu'ils prennent l'avion pour la côte Est. Donc c'était vraiment juste. Quand je pense que dès les premières semaines, quand on a testé les modules et que tous les modules étaient bons, aussi de voir que on voit ça d'un point avantageux, parce qu'on a des circuits tellement modernes, on peut toujours remplacer avec quelque chose d'autre qui ne marche pas, de la vieille électronique. Donc c'est très rare qu'on n'arrive pas à réparer quelque chose des années 60. Enfin, c'est tellement rare que c'est jamais arrivé sur ma chaîne. Mais donc on savait qu'on allait pouvoir trouver un moyen, puis on avait un FPGA entire, on avait une réplique en FPGA, donc ça allait, on allait trouver un moyen ou un autre. Quand on a su, après les quelques premiers jours, que tous les modules marchaient, sauf un ou deux, là on avait des... We got good vibes, right? Donc là, on l'a su assez tôt, en fait.
D'autres questions?
Bon, ça sort un petit peu du contexte de Apollo, mais je voulais savoir un peu qu'est-ce que vous aviez fait à Bell Labs, puis un peu vos travaux.
Moi, j'ai fait de la communication par fibre optique. Donc j'ai commencé par patouiller et faire les premiers circuits intégrés optiques, qui en fait ça a mis très très longtemps à devenir une application, mais maintenant c'est très très chaud, comme on dit.
Dans les terahertz, c'est ça? Les circuits dans les terahertz?
Pardon?
Un peu l'électronique dans les terahertz.
Oui, non, c'est des circuits intégrés optiques, donc des lasers, des modulateurs, des machins. Donc oui, c'est ça, c'est la radio, mais dans le terahertz, dans les centaines de terahertz. Donc on avait les premiers trucs qui faisaient comme la radio, hein, on mettait plusieurs fréquences ensemble, on démodulait, on fait les trucs cohérents. Et puis après, j'ai fait une compagnie qui a fait les premiers transpondeurs à 10 gigabits par seconde. C'est ça qui nous permet de tâcher en partie tout le matériel, avoir le beau labo. Et donc je fais toute ma carrière dans l'optique, qui est en fait 50% d'optique, et puis même pas 20% d'optique, et puis 50% de mécanique, et puis le reste c'est l'électronique microfréquence. Donc c'est un peu dans mes cordes. Donc tous ces beaux machins HP, c'est ce que j'utilisais dans le labo en fait.
Merci beaucoup.
That's the end of the conference.
No other questions?